In this video, we discuss velocity, speed, and acceleration for one-dimensional motion along a straight path. Let's say we've got a particle or a person moving back and forth along an x-axis. Well, the person's position as a function of time could be given by a graph that looks a little bit like this. And this is actually a very common quiz question. I might just give you the position function and ask you to graph the velocity and the acceleration, or the velocity, the speed, and the acceleration, and then ask you to describe the motion of the person or the particle that is given by that particular graph. Now, if I were given this graph on a test or a quiz, the first thing that I would want to do is define all of the branches, like write the equations for the branches of this piecewise function. This actually has 5 branches. We got one piece here, a linear piece here, a linear piece here, a linear piece here, and then another piece over here. This first piece and the last piece actually look very similar. They both look like part of a parabola. I notice that this curve goes through 0, 0, 1, 1, and 2, 4. Those are the coordinates of y equals x squared, or if t is our independent variable, y equals t squared, or if we're using x as the dependent variable, it'd be x of t equals t squared. But it's not the entire parabola, it's only that part of the parabola on the interval from 0 to 2. So I would say x is equal to t squared on the interval from 0 to 2. And then I added this subscript of a 1 because Desmos.com doesn't give us the option for separating those pieces of the piecewise function and typing it all at once. So I just graphed that piece for the first piece, and then I said, okay, on this piece, we go from 2, 4 to 4, 6. So we go up 2 and over 2 to get to another point on our line. So we can see that the slope of that line is just rise over run, which is just 1. 2 divided by 2, which is 1. And you can imagine if this were extended beyond t equals 2 and t equals 4, that line is going to cross here at t equals 2. So we get t plus, or not t equals 2, x of t equals 2. It's going to cross what would traditionally be the y-axis of t equals 2. So the equation is the independent variable plus 2, or t plus 2 in this case, but we're only interested in the part between t equals 2 and t equals 4. And then on this segment, between t equals 4 and t equals 7, we're assuming that t is time measured in seconds. The position is just x equals 6, x of t equals 6. So it's just a constant position the whole time. And again, that's the third piece, so I just wrote x sub 3. And that's the piece for that interval. And then on this line segment, we have a graph with a slope, or a line with a slope of, or in this segment, excuse me, we have a line with a slope of -3. We start at 7, 6, and we go down 3 and over 1 to get to the point of t equals 8, x of t equals 3. So we know that the slope is -3, and we know that the graph should pass through the point of x equals 7, y equals 6. So I have -3 times x minus, or t minus 7. That's the slope, which is the change in x divided by change in t times the change in t. And then we add the original x value to get the equation for x of t on that curve. So if you wanted to, you could think about extending that curve indefinitely, and then you'd say, okay, well, where does that cross the x of t axis? And it would cross at, what, 21 plus 6, x of t equals 27. But I was just thinking in terms of the slope or the equation of a line, or the traditional equation of the tangent line we've been using in other videos to write down that equation. And then on this one, we just see the y equals t squared graph, but it's been shifted over 10 units to the right, and it's been shifted down 3 units. So I just took t squared and I replaced the t with t minus 10 to move the whole graph to the right 10 units, and then I subtracted 3 to move the graph down 3 units. And I'm only interested in the part between t equals 10 and t equals 12. So I gave myself that interval of t values. And we want that endpoint for t equals 12, so we put a less than or equal to sign right there. Okay, so this is our graph. We say, okay, well, what's the velocity? Well, if I know that this is t squared, the velocity can be found just using the power rule. We're going to have 2 times t. So we have that as our derivative. Now on this piece, it's just a line segment. The slope was 1 because we go up 2 and over 2. So 2 divided by 2 is 1 is the slope. So x prime is just going to be 1. Actually, we should probably get rid of all those points. Just get rid of the labels. Just make the graph a little. And then on this line segment, our x value is a constant 6. It's a little bit easier to see if we add grid lines. Oh, goodness. Might be a little too much. It's quite a few grid lines. Let's see. Something like that. Now you can see that the x values are all equal to 6 there. So the derivative is just 0. The slope of a horizontal line is just 0. So we're on that line segment. On that line segment, our slope is 0. So I'm graphing that there. And then on this segment, from t equals 7 to t equals 10, the slope was -3. And then from t equals 10 to t equals 12, our slope was the derivative of that t minus 10 quantity squared minus 3. And we just use the chain rule for that. So 2 times the original quantity, which was t minus 10, times the derivative of the inside, which is just a 1. And so that is our derivative graph. A little easier to see if we get rid of the original function. Now, our original function had some sharp corners in it. Everywhere where the slope is different as the function approaches a particular t-value from the left and the right, we're going to have open circles on the derivative graph. We have a tendency to use closed circles on the ends, though. So the limit as t approaches 0 from the right exists when we're taking that derivative using a limit definition. We include the 0.00 in this case. And if the limit as t approaches 12 from the, I said that from the left over here, but what I meant was from the right, as if the limit as t approaches 12 from the left exists, for that limit definition of the derivative, we include that point as well. This is our graph of the derivative. And then, of course, this is piecewise linear, so it's very easy to see what the acceleration would be. If we want to graph the velocity, it's going to be almost exactly, or this is the graph of the velocity, excuse me. I guess we should call that v of t. Now, if we wanted to, we could also graph the speed. If this is the speed, well, everywhere where our function is non-negative, we would just keep those pieces exactly the same. So for the speed, I would just have the same graph as I would have typically have for velocity. So I'd have that piece and this piece and this piece, and then the last piece as well. But the only piece that's affected by the absolute value, when we take the absolute value of velocity to get the speed, is this piece that's has a speed of -3. You just take the absolute value of that part. Now we'll change the color so that I can distinguish the speed graph from the other graph. And then those two open circles really wouldn't fit anymore. So those were at 3 and negative, or the y values were -3, so we're just going to want them to be 3. That's speed. And then acceleration is the derivative of this. These are all horizontal line segments, so we're gonna have 0 acceleration here, here, and here. And then on this piece, the equation was just 2t, so its derivative is 2. And on this piece, the derivative is also 2. It's easier to see if we get rid of all these points. We'll probably change the label at that point, call this A of t instead of speed. Make sure that you exclude those points of discontinuity on the original velocity graph when you graph the acceleration. It's a little bit harder to see. It might be better to make it sort of bold. So that's our acceleration function. So the acceleration is 2 here and here. So that means our velocity is increasing the entire time, and with a constant acceleration of 2 meters per second squared if our speed is, or if our position is measured in meters. Now here our acceleration is 0, so that means we're dealing with constant speed. This is all easier to see or easier to imagine if we just graph that one-dimensional motion. Now this time when I graphed this particle, it's rather than a person, I wish I could graph a little person. I used separate colors or different colors for each segment of our piecewise function so that we could see what the results actually look like. These are the equations, the same equations from before. It's actually just one piecewise function with 5 different branches. Desmos does not allow us to type that in at the moment. But this particle is just moving back and forth on the x-axis. If we start at t equals 0, and then just hit the play button, you can see what happens to the particle. I think you're right. Excuse me. So let's look at the original function. So here's our function. So you can see that the position, now it's labeled incorrectly. Sorry. You can see that the position of a function of time is given by this. And so here, because our graph is curved, we can see that the function is, or the acceleration is actually positive. We're covering more distance as time increases. And so we have a positive acceleration here can also tell that it's a positive acceleration because the graph is what we call concave up. It just looks like a cup facing up on the interval of interest. So the particle starts from rest at time t equals 0, and then its speed gets larger and larger as it goes from t equals 0 to t equals 2 seconds. So in the first 2 seconds, the particle is speeding up, the velocity is increasing. The velocity is increasing with the equation of 2t. So at time t equals 0, the velocity is 0. At time t equals 1, the velocity is 1 meter per second, or 2 meters per second. And then at time t equals 2, the velocity is 4 meters per second. And then from t equals 2 seconds to t equals 4 seconds, the particle just has a constant speed of 1. So it's not accelerating at all. It just goes at a very constant speed. And then from t equals 4 to t equals 7, well, the position is just 6. So the particle or person, whatever it is, just sits there for 3 seconds. And then on this line segment from t equals 7 seconds to t equals 10 seconds, we can tell because the slope is -3 that the particle is moving backwards with a speed of 3 meters per second. So it's going in the opposite direction. But every second it's covering another 3 meters. And then at time t equals 10, the velocity is 0 again, and it starts to speed up. The velocity increases from t equals 10 when it's 0 to a larger velocity when t equals 12. So let's look at that. One-dimensional motion. Thinking of this as a particle on the x-axis, it's going to look like this. And all I've done to do this is just typed in those functions in a new graph. I've asked for the x coordinates to be defined by each of those branches of our piecewise function, and I made the y value 0. And if you want to, you can go to this little tool, little wrench here, and you can say, I want to see the x-axis, but I don't want to see the y-axis. I don't want to see the grid. I want everything to be nice and neat. I want the step size to be 1, so I wanted all the tick marks to be 1 unit apart on the x-axis. And that's how I got this little graph. Very easy to do. And then just hit play. You see it speeding up. Then it has a constant velocity from t equals, or when it's going from a position of 4 to a position of 6 meters. Then it just sits there for 3 seconds. Then it has a constant velocity of 3 meters per second as it goes in the opposite direction, and then it starts from rest, and then it speeds up as it goes from from x of t equals -3 to x of t equals 1. So the position is for some. I'm always thinking of a person. I wish I could draw a little line or a little like what is it? Stick man. I draw a little man here walking back and forth on the x-axis, but we can play that again. So it speeds up for the first 2 seconds, covers 4 meters essentially. Then from 4 to 6, in the next 2 seconds, it has a constant velocity. Then it has a constant velocity as it goes in the opposite direction. And then it speeds up from t equals 10. When t equals 10, the particle is located at x equals -3. And then when x is equal to, or when t is equal to 12 seconds, it's over here at x equals 1 meter. We're thinking of these as 1 meter apart. I hope that helps. Let me know if you have any questions.